Hello, George Romanic here. Today we are going to talk about Boltzmann distribution. I could not wait to share this lecture with you. Boltzmann distribution is one of the greatest achievements of physics, in my opinion. It is not as famous as Maxwell's equations, Navier-Stokes equations, Newton's laws, and so on. But in my opinion, it is just an astonishing result. The level of physical reasoning, the level of mathematical rigor, and the precision of the theory are just astonishing. And today we will develop that Boltzmann law or Boltzmann distribution. What is it all about? Well, in your room there is gas, air around you. And let us assume there is total energy of air in your room. And that could be total kinetic energy of all atoms. So the question is, how is that energy partitioned among these atoms? Is it possible, for example, that all atoms have no energy except one, and that one contains all energy, total energy of that system? Well, answer is theoretically yes, but in practice that is highly unlikely. Perhaps you would have to wait million ages of our universe to witness something like that. So you could say, well, is it possible that out of these trillions and trillions of atoms in your room, all of them have zero energy except three? Only three atoms have certain energy, and sum of these three energies is the total energy of air in your room. Well, again, in principle, it is maybe possible, but highly unlikely. What is more likely is that total energy is distributed among these particles, so certain number of particles has this amount of energy, another number of particles has a little bit less energy, another batch of particles has even less energy, and so on. So there is certain distribution of energies among these atoms. Well, the question is, what is that distribution? Boom. That's Boltzmann distribution. So that is the most likely distribution of energies among atoms. In other way, we will see what is the probability that this many atoms have that much energy, this many atoms have that much energy, and so on. The theoretical answer to that question is Boltzmann distribution. And then from Boltzmann distribution, we can go one step further and develop the Maxwell-Boltzmann distribution of speeds and velocities of atoms in a gas. But that will be a separate video. First, we start with Boltzmann law. Let's start. Consider a system of n particles that are behaving like an ideal gas. And here, perhaps this is your room or basement. And there are trillions and trillions of atoms or molecules in this box. They have temperature T, volume of your room or this box is V, and there is total energy that these particles have, and that is E. And there are n of them. What is important to realize is that not all atoms have the same energy. Some are more energetic than others. So, suppose that n small subscript 0, n0 atoms are at some energy level epsilon 0. We can also say, suppose there are n1 atoms that are at energy level epsilon 1. There are n2 atoms that are at energy level epsilon 2, and you get the point. What we mean by this is the following. Say we have 4 identical particles. That means total number of particles n is equal 4. And in the context of kinetic theory of gases, atoms or particles are indeed identical. And say we have total of 4 energy states that I will represent in the following way. If they are discrete, this could be energy level epsilon 0 equals 0. The next energy level could be here epsilon 1 equals 1. Here we have the next energy level epsilon 2 equal 2, and here we have epsilon 3 equal 3. So these are energy levels, and to make this problem simple, I made separation between energy levels being constant, which is 1. This level is 1 more about 0. This level is 1 unit more above level below, and so on. This doesn't have to be the case. Maybe this level, top level, epsilon 3 could be 10. But just for simplicity, we will look at it like that. And now let us say there are 4 particles. These particles are maybe distributed among these energy levels, that we have particle 1 sitting over here, particle 2 and particle 3 being over here, and let's say particle 4 occupies this energy level. If we calculate this total energy, what will it be? It will be 0 for particle 1 because it's energy level 0, plus it will be 1 for particle 2, plus it will be 1 for particle 3, plus we don't have anything at the level 2, and it will be 3 for this particle 4. So the total is 5. But this is just one of the possibilities of how these particles could be distributed among these 4 energy levels. We could have also the following distribution, that particle 1 is sitting at the top energy level, particle 2 is maybe sitting at the energy level 2, and particles 3 and 4 are here at the 0 energy level. If we calculate total energy of this system, we will get, well, particle 1 has 3 units of energy, plus particle 2 has 2 units of energy, plus nothing is on energy level 1, and plus we have 0 plus 0 for particles 3 and 4, and we again get 5. For good measure, let's look into one more case. Possibility number 3, where maybe we have particles 1 and 2 being here, particle 3 sitting here, and particle 4 also sitting here at energy level 1. If we calculate total energy, we will get for 1 and 2 particles, that's energy level 1. So 1 plus 1. Particle 3 has 2 units of energy, and then particle 4 has also 1 unit of energy, and we again get 5. So as you can see, there are many different cases or possibilities that we are allowed to redistribute these particles as long as total energy is the same. And these different possibilities are technically called microstates of this system. In doing this exercise, clearly there are 2 constraints that are placed on our system. Constraint number 1 is that total number of particles is n, and it's a fixed number. What does that mean? That means in this box where we want to redistribute these particles, we are not allowed to bring more particles from outside or remove atoms that are already in this box. So the total number of particles in the box is unchanged, very reasonable constraint. And the second constraint that is equally reasonable is basically what we calculated over here in these three examples. And that is that the sum of particles that are occupying given energy level times the energy of that level is the total energy of the system. And that is also constant, as we indicated here. That means this system is in equilibrium. There is no supply of, let's say, heat or something else from outside, radiation. Temperature is well defined for this system. System has fixed total energy, and now the question is, how are particles in this system going to redistribute themselves in terms of their energy levels of this system? So what would be the total number of these microstates that we can distinguish? And by distinguish we mean, in this particular case, let's say, if I swap 2 and 3 over here, that's the same as having this configuration over here. We are interested in total number of distinguishable microstates. And we often, historically, call that capital W. That is the total number of distinguishable microstates in this system. Now, to calculate this W, and this is where the fun begins, we have to dwell into mathematics and the theory of probability, in particular theory of permutations. And now I will talk a little bit about permutations so you can properly understand how we get this W, total number of different rearrangements of this system. Permutations are ordered list of all elements in a set, or they represent the number of ways a particular set can be arranged. Let us take a set of 1. This is a set of 1, and we see that the total number of arrangements is equal, 1. There is nothing else I can do with this, let's say, number A, element of this set, than what it is now. But if we have a set of 2, A and B, then the number of arrangements of this set is equal to. Why? Well, because in addition to AB, I could also have BA. I could permute these elements like that. Let us take set of 3, A, B, and C. Total number of arrangements in this case is 6. Why? Well, in addition to this arrangement, we could also have BAC, where I swapped the order of A and B, kept C as it is. Then we could have BCA, where I swapped now these two. Then we could have ACB. We could have CAB. And lastly, we could have CBA. So you can see, as you are increasing number of elements in a set, the number of permutations starts to increase significantly. And we say that if a set has n elements, then the number of this is number of elements. then the number of permutations is n factorial, where this is equal 1 times 2 times 3 times 3 dots times n minus 1 times n minus 2 times n minus 1 times n. This is factorial function where we indicated with this exclamation mark. It is pretty easy to understand why n factorial, that is written like that, is a good representation of permutations, namely the number of ways we can rearrange elements of this set. Let's take this simple case n equal 2. You can see that n equal 2, n factorial would therefore be 2 factorial, and that would be 2 times 1, and that is 2. But let us see at this 2 times 1. If we have two elements in the set, then element number 1 can be in two positions, and consequently there is only one position where the element 2 can be, so 2 times 1 equals 2. Similarly, if we have three elements in a set, then factorial would be 3 factorial, and that is 3 times 2 times 1, and that is 6. But what I want to say here is that there are three positions where the first element of the set can be placed. Then there are only two more positions where the second element of the set can be positioned, and then there is consequently only one more position where the last element of the set can be positioned, and that's how this factorial function was developed. At any rate, what is also important to note is that by definition, factorial of 0 is 1. But what we described here is the case when all elements of our set are different. But if we go back to our kinetic theory of gases, you will see here that all elements don't have to be different. For example, 2 and 3 here are the same in terms of their energy content. So they don't contribute differently if I swap 2 to 3 over here. So in our case, we do have total of n elements, objects, particles, but n0 are alike on energy level 1, n1 of them, in this case 2, are alike at energy level 1, and so on. You get the point. Here we have 3 of them that are alike at the energy level 1. Allow me to demonstrate this further because sometimes it can be confusing. Let us take my name, for example, DJORDJE, George. Strange spelling of my name in Serbian, that by the way would be like this in Cyrillic, or like this in Latinic, where this J is DJ. But this is not so important. Let's look into this. And let's say this is my set. And you will agree that this set has 7 elements. 1, 2, 3, 4, 5, 6, 7. But out of these 7 elements, I have 2 Ds and I have 2 J's. If I swap this D with that D, that's the same set. Or if I swap this J with this J, that's the same arrangement of this set. Well, these 2 Ds can be arranged in 2 factorial ways, and these 2 J's can be arranged in 2 factorial ways. Which means that the total number of distinguishable perturbations of this set is equal 7 factorial, which is the total number of perturbations, but reduced for these 2d's and 2j's. 2d's times 2j's factorial. And now we know how to calculate this. This would be 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 2 times 1 times 2 times 1. If you calculate this, you will get 1260. Similarly, if we take a set of subscribe, notice that in this set, which by the way has total number of elements that is 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, there are 2 S's and there are 2 B's, so the total number of unique arrangements is 9 factorial divided by 2 factorial times 2 factorial, which accounts for 2 S's and 2 B's. And if you calculate this over here, you will get 90,720. So that's the number of ways you can subscribe on my channel, pretty much. Imagine if a theoretical channel like this one that goes deep into theory and disregards everything about beauty blogging will ever reach 90,700 subscribers. Now, equipped with this knowledge, let us go back to our case of different energy levels and different number of particles occupying these energy levels. So what we have here is we have a total of n particles, out of which n0 are occupying energy level epsilon 0, and they are the same, these n0. n1 is occupying energy level epsilon 0, and all these n1 are the same, and so on. And we want to find total number of these perturbations W. Well, knowing this and knowing this, we can now very easily conclude that this W has to be permutation of all n particles reduced for the number of n0 particles that are occupying energy level epsilon 0, reduced for n1 same particles that are occupying epsilon 1, times 3 dots, which is basically the number of energy levels that we would have, which I don't know. We don't know how many energy level there is in a gas. But this is the formula that we have here. And this is the start of beautiful mathematics that now continues in this video that of course will be long but absolutely beautiful, with the result that will be one of the greatest things you ever saw in your life. Now, this is the total number of permutations, total number of rearrangements of these n particles in this system. But what we want to know is what is the most likely arrangement of these particles, or more technically, what is the most likely microstate. Let us again visualize what we mean by this before we proceed with mathematics. Let's say we have that box that we investigated, which could be your room. Well, in principle, because we say there is n particles, and these n particles have total energy E. In principle, we could say that all particles are completely static, but there is one rebel particle that has all energy for itself. Is this possible? Well, in principle, yes, but not very likely. You could wait for the age of the universe and even more, and this would never happen with the number of particles in your room. Instead, what is more likely is to have this same number of particles that have total energy E, but this one, now in terms of velocity, but that could be translated into energies, as we will do later. You know, they have different energies. This one has smaller energy than this one has larger, this one has something, but overall they have some distribution of energies that is not very unlikely, like this figure on the left. And how do we find the most likely microstate or distribution of energies of these particles? Let us start developing this beautiful mathematical theory on this new sheet of paper. We have our function that we need to maximize. It would be logical to take first derivative and set it equal to 0. But because W is enormous number, it is more useful, what Boltzmann figured out, to take derivative of the logarithm of this function because W is so large, and then set that equal to 0. How do we know that W is so large? Did I convince you? Of course I did. On previous page we had set that had 9 elements, subscribe, namely set of subscribe letters, and it was already 90,000 combinations. Now imagine if you have trillions and trillions of atoms in your room. What is this number? It's absolutely something that our brains cannot comprehend. So that's how huge that number is. But now, when we know this, we need to be actually careful. And here is where we need to remember my previous video on Lagrange multiplier. What do I mean by that? Well, we need to find maximum of this function. But we have 2 constraints that are set on our system. And you will remember that constraint number 1 was that the sum of all particles is a constant n, total number of particles in the system. And the constraint number 2 was that the sum of Ni times epsilon I is equal total energy E. We absolutely need these constraints, because without these constraints you would get results that are either trivial or make no sense. And what do I mean by that? Well, I mean, if you just maximize this function, you might get that the maximum is when you don't have any particles in your box, because you allow particles to escape. Or maybe the maximum is achieved when energy is 0, you just take all energy from the box, and so on. We don't want that. We want to maximize this function, but keep the number of particles in the box constant and total energy constant, which also means that the gas in the box in your room is in equilibrium. It has well-defined temperature. Now, of course, we could right away add these constraints to our problem, but it is beneficial to first manipulate this equation to get a nice expression that we can work with. So let us see first what is ln of W before we take this differentiation. Well, that is ln of this over here, n factorial divided by n0 factorial, n1 factorial times 3 dots. And that is further equal ln of n factorial minus ln of n0 factorial times n1 factorial times 3 dots. But this is further equal ln of n factorial minus ln of n0 factorial plus ln of n1 factorial plus 3 dots. Or we can further write this, that is ln of n factorial minus, well, this is just sum over all i's ln ni factorial. Now this expression can be simplified using the so-called Stirling approximation. For large x, ln of x factorial can be represented with pretty good accuracy as x ln x minus x. And because, again, we are going deep on this channel, I will provide you with quick and dirty proof of this claim. And this proof is the following. If I take ln x factorial, well, that would be ln of 1 times 2 times 3 times dot times x. And that is equal ln 1 plus ln 2 plus ln 3 plus 3 dots plus ln x. But this is further equal sum, when sum j goes from 1 to x, ln of j. This over here clearly, because when j is 1, this is 1. When j is 2, this is 2. When j is 3, this is, ln 3 and so on. You get this. But now this can be approximated, this sum can be approximated as an integral between lower limit 1 and upper limit x of ln x dx. And I'm not going to now spend time solving this integral. This can be solved using integration by parts easily. But if you do that, then the solution of this integral is x ln x minus x. And that is in the limits between 1 and x. And this is further equal x ln x minus x, that's when we insert the upper limit, minus 1 ln 1 minus 1, but ln of 1 is 0, and we get that this is equal x ln x minus x plus 1. But this plus 1 can be neglected because if x is very large, and in our case you have trillions and trillions of atoms in your room, who cares if it is trillion plus 1 or trillion? So we can just neglect this term, and look, our quick and nasty proof is completed. So using this Stirling approximation, we go back to this expression and we write that this is further equal n ln n minus n, that's this term over here, minus sum over I of ni ln ni minus ni. And this is now further equal of n ln n minus n minus sum over dummy variable I ni ln ni plus minus, and minus will give me plus sum over I and I. But look, this sum over I and I is n, and that will cancel with this n over here. So we are making some progress here, which means that this ln w is equal n ln n minus sum over I ni ln ni. And this is our function that we want to now maximize using this method over here with these constraints. You remember in my previous video on Lagrange multiplier, we call this function objective function, and these are called constraints. And you will kindly remember from that video that if we have objective function f(x,y), let's say, and we have two constraints g of x and y are some independent variables, and we have second constraint age of x, y, so these are constraints, then we know that we have to write nabla f is equal lambda 1 nabla g plus lambda 2 nabla h, where lambda 1 and lambda 2 are the so-called Lagrange multipliers. All this is extensively explained in my previous video. So first what we need to do is now finally differentiate this ln w. And d of ln w is equal d of n ln n minus sum over I ni ln ni. But notice that n is a fixed constant, so differentiation of this term will simply be 0, which means that we get sum over I differential of ni ln ni, which is this term over here, with minus, of course. And because both differentiation and sum are linear operators, I can switch the order, which I did here, of these two. Now I differentiate this as a product minus sum over I. I will first have d ni ln ni, so that's this, plus I copy the first one, ni, and I differentiate logarithm, which is clearly 1 over ni times d ni, because this is a differentiation of a function. Now notice that these two cancel, which is very good, and we end up with the following, that this is all equal to sum over I with negative sign. I can factor out dni, and I will get here ln ni plus 1 dni. Now we need to carry out differentiation of our first constraint. So we have that d of the sum over I ni minus n, that is our constraint, is equal sum over I dni, because again differentiation of n is 0, this is fixed constant. Differentiation of our second constraint is sum over I ni epsilon I minus total energy E, and that is equal, once again, sum of epsilon I dni, because total energy is fixed, and also, this is important, also energy levels are fixed. This is what I demonstrated here schematically. We have fixed energy levels, but the particles can jump between these fixed energy levels which means that this is constant. So we write that our object function minus sum over I ln ni plus 1 dni is equal Lagrange multiplier 1 times this first constraint sum over I dni and plus second Lagrange multiplier times the differential of the second constraint, which was epsilon I dni. Or I can move these two on the left side and I will get negative sum over I ln ni plus 1 dni minus lambda 1 sum over I dni minus lambda 2 sum over I epsilon I dni equals 0. Now I will multiply this equation with negative 1 and group terms around dni, because I have dni everywhere, and I will get that the sum over dummy variable I is ln ni plus 1, that's this, plus lambda 1, that's this, plus lambda 2 epsilon I, this, everything multiplying dni is equal to 0. And this is constant, so this plus this is also constant, and I can call it alpha. Which means that the sum of ln ni plus this alpha plus lambda 2 epsilon I is equal times dni is equal to 0. And this is the final equation. Now when we look into this equation, we see that this can be equal to 0 if this term over here is 0. Namely, if ln ni plus alpha plus lambda 2 epsilon I is equal to 0. Or ln ni equals negative alpha plus lambda 2 epsilon 0. Now I will run with exponential function through this expression, and I will get that ni is equal exponent to negative alpha plus lambda 2 epsilon I. And this is already absolutely astonishing result, because this is number of particles in the ith energy level. Let's take sum of this equation over all indices I. So that will mean that we have sum over I ni equal sum over I e to negative lambda plus alpha plus lambda 2 epsilon I, but that is equal e to negative alpha, because this doesn't depend on our summation, times sum over index I e to negative lambda 2 epsilon I. But we already know that this sum of ni is capital N, which means that e to negative alpha is really equal n divided by the sum over I e to negative lambda 2 times epsilon I. And this function actually has very special name. It's called partitioning function. Substituting this over here, we can finally write Ni is equal capital N e to negative lambda 2 epsilon I divided by the sum over I e to negative lambda 2 epsilon I. We can also write this in terms of probabilities if we don't want number, because Ni divided by this capital N is probability of this ith state, and that would be e to negative lambda 2 epsilon I divided by the sum over all states lambda 2 epsilon I. And this is one of the greatest achievements of mathematical physics, statistical mechanics, kinetic theory of gases. This is Boltzmann distribution of energies that is basically nothing else but counting. Let us now see the greatness of this Boltzmann distribution. To do that, I prepared a small script in MATLAB that plots these two figures. On the left, you can see that we have only 13 atoms in our box, in our system, and we allow these atoms to be distributed among 47 energy levels. You will notice that probability of an atom being in a given energy level or energy state is given by this exponentially decaying function. On the right, we can see how function, which is black line, that is Boltzmann distribution, fits this empirical counting, basically. So you can see that this function that I fitted here is exactly of this form, because this denominator, namely partitioning function that I said, is a constant. This is a number, and we will determine that number at some point in next videos. So this could be some constant C1. Well, epsilon I is this EI, and this is also constant. Namely, lambda 2 can be constant 1 over C2. So here I just provided values of these constants. If you want to replicate this, it's totally not important. But what is important is to see how perfectly this distribution fits the arrangements of these atoms for different energy levels. And purposely, here I plotted probability, and here I plotted average number of these atoms. So probability would be in this form, and number of atoms would be in this form over here. At the very end, I would like to say that in one of the future videos, we will explicitly demonstrate that this constant lambda 2 is really 1 divided by kT, where K is Boltzmann constant and T is absolute temperature. But that is story for another video. This video was long, but it was worth watching. This was the most complete derivation of Boltzmann distribution on this platform. Now, when you are sitting in your room, in your car, park, you can imagine air around you, and you can also imagine Boltzmann distribution, namely how there is a certain state that is most probable, and that state is described by Boltzmann distribution. And by that state, I mean there is certain number of atoms that have this much energy, a little bit less atoms that have a little bit more energy, even less number of atoms that have higher energy, and so on. Cascading is described by Boltzmann distribution. In the next few videos, we will first demonstrate that this Lagrange multiplier is nothing else but 1 divided by Boltzmann constant and absolute temperature. And then we will use that knowledge to derive Maxwell-Boltzmann distribution of speeds and velocities of atoms in a gas. Until these videos, goodbye.